Today we're going to look at section R.7, Radical Expressions. In example 1, let's write each root using exponents and evaluate. For this we'll need a formula. X raised to the m over n is equivalent to the nth root of x raised to the m power. So this is a formula that we should memorize. It allows us to convert from a rational exponent to a radical, or from a radical to a rational exponent. In this example, we're looking for the cube root of 27. This can be rewritten as 27 raised to the 1/3 power. Now, in order to evaluate this, we can do it with a calculator. I'll enter 27 in my calculator and then press the caret button here, and then we'll raise it to the 1/3 power. So use a parentheses and enter 1 divided by 3 inside that set of parentheses, and this is 27 raised to the 1/3 power. If you enter that, you get 3. So the cube root of 27 is equivalent to 27 raised to the 1/3, or it's equal to 3. Again, enter 27 raised. I like to put a parentheses, then do 1 divided by 3, then close off that parentheses and click enter, and you'll be able to get our answer 3. For part B, we're going to use the same formula. We're going to convert this radical to an exponent. Notice that the negative is on the outside, so we'll leave it on the outside, and then we'll have 10,000. Raise that to the 1/4 power. Notice that the 4 is in the index, and there is an invisible 1 exponent out here, just like in part A. There's an invisible 1 out here, and we're using our formula. Now we could put 10,000 raised to the 1/4 power on our calculators. To do this question on the calculator, you want to put the negative symbol first. So I'm going to use this negative symbol here. Don't use the subtraction symbol. You'll get a syntax error from that. Put the negative symbol, then you're going to enter 10,000. So we have the negative symbol with the parentheses. We'll enter our 10,000. You do not need a comma. Enter the 10,000. Then press the caret button here and raise it to the 1 divided by 4 power in parentheses and click equal, and you will get your solution. And our solution to this is -10. So double check with your calculators, make sure you can get -10 from part B. Part C, let's rewrite this as -216 raised to the 1/3. Again, there's an invisible exponent of 1, so this is equivalent to -216 raised to the 1/3 power. And to enter this, you want to be extra careful. I want to make sure to put parentheses first, then this negative symbol. So that's -216. And then I'll close it off. So this is -216 inside a set of parentheses. We're going to raise that to the 1/3 power. So caret again, raised to the 1/3 power with parentheses, and enter this, and you will get your solution. And for our solution, we have -6. Again, double check with your calculator that you can get -6. If you have a different calculator and you don't know how to do this, send me an email and I'll teach you how to use it on your particular calculator. For part D, we have a negative on the inside. There's a negative on the inside, and the index is even. We cannot take the fourth root of a negative number because the index is even. Think about this. What number do you raise to the fourth power gives you a negative 81? There is nothing that's going to work because this number raised to the fourth has to be positive. A positive number cannot ever be equal to a negative number. So this has no real solution. This has no real solution. There's no real number that will work for part D. If you were to try to enter this on your calculator, you'll get something like domain error. Example E, we want to rewrite using exponents and then evaluate this. We're going to use the same formula as before. This is equivalent to 125 over 512 raised to the 1/3 power. Now I could also use the property of exponents. This is equivalent to 125 raised to the 1/3 over 512 raised to the 1/3. And of course, we know how to use our calculators now. We can enter this in our calculators. This is just 5 for 125 raised to the 1/3. And 512 raised to the 1/3 is just 8. So practice with your calculators. Make sure you get a 5 on the top and an 8 on the bottom. For part F, there's a negative floating in the front. So let's put that negative in the front. A parentheses negative 243 raised to the 1/5 power. Type this into your calculator. Make sure you have parentheses around here and use the negative that has a parentheses around it and then raise it to the 1/5 power. This gives me negative 3, and now I can deal with that negative. This is a positive 3. In example 2, I want to convert these into a radical and then simplify. So let's recall that formula. X raised to the m over n is equal to the nth root of x raised to the m power. So we're going to use this formula again, and we're going to write these as a radical. This is equivalent to the fourth root of 16 raised to the 3rd power. The denominator is going to go into the index, and that 3 goes into the exponent. So we can use our calculators to find the fourth root of 16. To do that, you'll enter 4, press the second button, then the caret button. So what you'll see is 4 and this tiny little x here inside a radical. So this 4 is saying this is the fourth root of, and we'll enter 16. Then press equals, and you should get your answer for the fourth root of 16. The fourth root of 16, if you do the calculator, would be 2. So this is equivalent to 2 cubed, and of course 2 cubed, I can enter that or do it in my mind, that's just 8. For part B, this is equivalent to the cube root, we know the index is 3 because that's in the denominator, of 64, and we're going to raise that to the 2nd power. If I want to find the cube root of 64, the inside of the parentheses, first you want to press 3, then second, then the caret. What that's going to do is have something that looks like this, a 3x and a radical symbol. So that's the cube root, and you want to enter a parentheses for the negative, this negative here, and then put 64 and press equal. And when you press enter, you will get negative 4. Make sure the inside of the parentheses is negative 4, but we still have to square this, and that's just positive 16. For part C, notice that there's a negative on the outside, but it's not affected by that radical. That 3 over 2 only influences the 121. This is equivalent to negative 121 raised to the 3 halves. So I can change this to negative the square root of 121 cubed. We know the square root of 121 is 11. This is equivalent to 11 cubed, or negative 11 cubed. We'll enter negative here with the parentheses around it. That's going to be negative, and then we'll enter 11. And then we'll raise that to the 3rd power and press enter. This is equivalent to negative 1,331. So double check with your calculator that you can get negative 1,331. In part D, let's rewrite this as a radical. If you ever forget, remember that denominator is going to be in the index up here, and the y is going to be on the inside with an exponent of 7. This is the 8th root of y to the 7th. You can also write it as the 8th root of y to the 7th. So these two are actually equal. If the 7 is on the outside, that's the same if 7's on the inside. So just be aware, some textbooks use the first format and some textbooks use the second format, but they're equal. Let's rewrite these in radical form and simplify. Just remember this 4/5 only influences the z. So I can rewrite this as 7, the 5th root of z raised to the 4th power. That's the simplified form. Or I could also write it as 7, the 5th root of z to the 4th. So again, the 4 could be on the inside of the radical or it could be on the outside, but it's equivalent. For part F, this negative 1/4 only influences the q. So I can rewrite this as 12 over q to the positive 1/4. Recall my negative exponent rule, x to the negative n is equal to 1 over x to the positive n. So I'm using this formula to rewrite our expression. I can rewrite this as 12 over the 4th root of q. For part G, again the index is going to be 6, so this is the 6th root of 5x plus 2y raised to the 1, but we don't really need it because we have an invisible 1 right here. In example 3, we're going to convert these radicals to exponential form. Recall x to the m over n equals the nth root of x raised to the m. Now what that means is I can convert from a radical to an exponent as long as I make sure the index is in the denominator and the numerator is the exponent on the top. This is equivalent to n raised to the 3/7 power. For part B, we have the 4 is in the index, so this can be written as 10x raised to the 1/4 power because there is an invisible 1 out here. And that's part B. For part C, notice this 4 only affects this part of the expression. The 15 has to stay on the outside, and r can be rewritten as 4/3. This 3 is in the denominator. For part D, this radical only affects the radicand here on the inside. So the negative 2 has to be in the front. We have 3x squared is now raised to, the numerator has to be 8, the denominator has to be 5. I could simplify this a little bit further by distributing that 8/5 to this exponent of 1 and that 8/5 to this exponent of 2. This is equivalent to negative 2 times 3 raised to the 8/5 power. Again, there's an invisible exponent of 1. 1 times 8/5 is 8/5. And we have x raised to the 2 times 8/5, which can be simplified to 16/5. This is our expression, negative 2 times 3 raised to the 8 fifths times x raised to the 16 fifths. For part E, there is an invisible exponent of 1. Let's rewrite this as an exponent, r squared plus s to the 4th raised to the 1/3 power. And that's the most simplest form for part E. In example A, let's simplify z to the 6th. We're taking the square root of z to the 6th. I can rewrite this as the square root of z times z times z times z times z 6 times. Now the reason I'm doing this is to show you a shortcut. Notice that we're taking the square root. So we're looking for the index here being 2. So think about the square root as taking groups of 2. If I look at the groups of 2, notice that we will have 3 groups of 2. When we take the square root of this part, the square root of z times z is actually z. The square root of z times z is z again, and z times z, if I take the square root, is z. This is equivalent to z cubed. What this is saying is if we look at the groups of 2 for z to the 6, we would have 3 groups of 2. And that's where I get this exponent from. Another way to think about this is we're taking that 6 and we're dividing it by 2. This is equivalent to saying the square root of z to the 6 is the same as z to the 6 divided by 2, or z cubed. So there's more than one way to think about this problem. We're taking the square root of z to the 6 is the same as 6 divided by our index 2, and that's where we get z cubed. Or I could think of it as looking for groups of 2, and there are 3 groups of 2. For part B, we're going to use the same idea. This is equivalent to z raised to the 7 over 7, or I can say this is z to the 1, or just z. For part C, we know the index is not there, so we can assume it's a 2. This can be rewritten as 81 r to the 8th, s to the 10th, raised to the 1/2 power. Now we can distribute that 1/2 to each of the exponents. The exponent for the 81 is a positive 1. This is 81 to the 1/2, r raised to the 8 times 1/2, s raised to the 10 times 1/2. 81 to the 1/2 is the square root of 81, or I could enter in my calculator, that's 9. 8 times 1/2 is 4, so this is r to the 4th. And 10 times 1/2 is 5. Our solution for part C, 9r to the 4th, s to the 5th. Now be careful part D. Part D is not going to be a no real solution case because this negative 3 is raised to the 4th, so the inside is actually positive. So we can take the 4th root of a positive number. Negative 3 to the 4th power is positive 81. This is equivalent to the 4th root of 81. I can rewrite that as 81 raised to the 1/4. Just enter that in our calculators, and our solution is 3. In part E, let's rewrite this as an exponent. This is equivalent to m raised to the 10 over 5, or m squared. 10 divided by 5 gives us 2. For part F, we will rewrite this as 3x minus 4 raised to the 2nd power divided by 2, and this simplifies to 3x minus 4, and we no longer need the parentheses. This simplifies to 3x minus 4. For part B, notice that this is a trinomial. I'm going to use the diamond method. Let's enter 25 for the top. We're using the diamond method, and the negative 10 for the bottom. What two numbers multiplies to get positive 25, but add up to get negative 10? The two numbers are negative 5 and negative 5. This can factor as x minus 5 times x minus 5. Or I could rewrite this as x minus 5 squared. And notice that this is the square root of a squared term. So I could write this as x minus 5 squared divided by 2. And this simplifies to x minus 5 raised to the 1, or just x minus 5. In example 5, we need another formula. This formula is the nth root of a times the nth root of b is equal to the nth root of ab. What this formula is stating is if we have the root of a number times a root of a number with the same index, we could just combine the radicands together into one big radical. For part A, we're going to do that process. This is equivalent to the square root of 5 times 45. We can multiply 5 times 45. This gives us the square root of 225. And we could use our calculators to find the square root of 225. That's equal to 15. For part B, we'll use the same process. The index are the same, so we can combine it to one big radical. We have n cubed times n squared on the inside. Now what do we do with the exponents when we multiply these two? We have to add them. This is the fifth root of n to the fifth. And this simplifies to n raised to the 5 over 5. Or it's equal to n. For part C, we'll need a different formula. The nth root of a over b is equal to the nth root of a divided by the nth root of b. This formula means if I take the nth root of a fraction, just take the nth root of each of the terms separately. This is equivalent to the square root of 11 over the square root of 169. I can't do the square root of 11, we'll leave that alone, but I know the square root of 169 is equivalent to 13. In these examples, we'll use the same formula. The nth root of a over b is equivalent to the nth root of a divided by the nth root of b. Let's rewrite this as the sixth root of a over the sixth root of b to the 12th. Now, I can simplify the bottom as b raised to the 12 over 6. And the top, we can't do anything, we'll leave that alone. This simplifies to the sixth root of a over b raised to the second, or b squared. For part E, let's work our way from the inside out. I can rewrite the fourth root of 17 as 17 raised to the 1/4 power. Now this is equivalent to 17 raised to this exponent of 1/4, and we're going to divide that by this exponent of 5. So this is 17 raised to the 1/4 divided by 5, which is equivalent to 17 raised to the 1/4 times the reciprocal, and I can simplify this to 17 raised to the 1 over 20th power. That's a good solution for part E. You could rewrite this as 17 raised to the 1 over 20, or if you want it as a radical, this is equivalent to the 20th root of 17. For part F, we can rewrite this as 8 raised to the 1 over 6 power divided by 2, and that is equivalent to 8 to the 1 over 6 times 1/2, or 8 raised to the 1/12. And I can also simplify this as a radical if I wanted to, as the 12th root of 8. So there's two ways to write it. You could write it as a rational exponent or as a radical, a rational exponent or as a radical. Now you might have also noticed that if you multiply 5 times 4, we get the 20, and if we multiply 2 times 6, we get the 12. So that's also another way to do these types of problems. In example 6, I'm going to do it in a slightly different technique than in the textbook. For part A, I like to use the factor tree to break down 288. This can be broken down into 2 times 144. And 144 can be broken down as 12 times 12. The 12 can be written as 2 times 6. The 6 is 2 times 3. And the other 12 can be written the same way. 2 times 6. And the 6 breaks down to 2 and 3. Now the numbers that are used to multiply to get 288 are these numbers. These numbers cannot be broken down any further. They're known as our primes. This now can be rewritten as the square root of 2 times 2 times 2 times 2 times 2 for 1, 2, 3, 4, 5 2's, and we have 2 3's. Now recall that the index is a 2 because it's invisible. We are taking the square root, so we're looking for groups of 2. Notice that the square root of this part is 2. The square root of this part is 2. The square root of this part is 3. So put those in front of the radical. Whatever does not have a pair, leave that on the inside. Now I can simplify the front terms as 12. Our solution is 12 times the square root of 2. This is the simplified version of the square root of 288. For part B, we'll use the same process with 125. Let's break down 125 as 5 times 25, and 25 is 5 and 5. I can rewrite this as negative 8 times the cube root of 5 times 5 times 5. Notice that this index is 3. We're looking for groups of 3 now. The cube root of 125, I know that's just 5. This is now negative 8 times 5, or negative 40. For part C, we will break down 128. 128 is 2 times 64. 64 is 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. So there's a lot of 2's in 128. There is in fact 1, 2, 3, 4, 5, 6, 7 2's. This is equivalent to the cube root of 7 2's a to the 6th, b to the 8th, c to the 10th. For part C, we're looking for groups of 3. Notice the cube root of this set is 2. The cube root of this set is 2. And we have a 2 left on the inside. The index is still 3. Now, how many groups of 3 are there in a to the 6th? I can divide 6 by 3 to get 2. I know there's 2 groups of 3 in 6. 6 divided by 3 gives us 2. There's 2 groups of 3. Now, how many groups of 3 are there in b to the 8th? 8 divided by 3 is not a nice number. It is 2 with a remainder of 2. That tells me I have two groups of 3 for b to the 8th, but there's two b's left on the inside, so we'll leave b squared on the inside. For 10, I can divide that by 3, and I have 3 remainder 1. Now, that means we have a c cubed on the outside. I have 3 groups of 3 in c to the 10th with a remainder of 1. So there should be c to the 1 on the inside, or just c. Now we can simplify this a bit. 2 times 2 gives us 4. This is 4a squared, b squared, c cubed times the cube root of 2b squared c. So this is a really nice trick. We're using division to find out how many groups of 3 there are, and whatever is left is going to be the exponents on the inside. What is the whole part is the exponents on the outside. For example 7, we can only add or subtract radicals if they have the same index and the same radicand. If they have the same index and the same radicand. In part A, they do have the same index. The index is both 2, and the radicands are exactly the same. The number on the inside is the same, so we can subtract these two. This can be written as 14 minus 11 times the square root of 5p cubed. 14 minus 11 is equal to 3. This simplifies to 3 times the square root of 5p cubed, and we can't simplify this any further. For part B, the index is the same, but the radicals are different. So we need to simplify this a little bit before. Let's break down 75. 75 is 3 times 25, 5 times 5. So this can be written as 3 times 5 times 5 for 75. If you're not sure, multiply it out. Make sure it's 75. This is ab cubed for the first radical. We can simplify the second one as well. 12 can be broken down as 2 times 6, and 6 is 2 times 3. This can simplify now to negative b times the square root of 2 times 2 times 3 times ab. Now we're looking for groups of 2. I have a group of 2 here, and I have a group of 2 here. The square root of 5 times 5 is 5. We have a 3 left over. Now, A does not have a group of 2, so we'll leave that on the inside. B cubed. I can divide 3 by 2 and know there's one group of 2 with a remainder of 1. That means we have a B on the outside and a B left on the inside. There's one group of 2 with a remainder of 1 on the inside. Minus B. And this square root of this part is 2, so we'll write it as 2b times the square root of what's ever left, and that's 3ab. Notice that they have the same radicands, they have the same index, so we could add the numbers in the front. This is 5b minus 2b times the square root of 3ab. 5b minus 2b is 3b. And we'll leave the radical alone. This is our solution for part B. In example 7, we'll break down 81 and 24 using our factor tree. 81 is 9 times 9, 3 times 3. And so 81 is 3 fours. For 24, that's 2 times 12, 2 times 6, 2 times 3. 24 is 2 times 2 times 2 times 3. Now you might have a different factor tree, but your numbers should be exactly the same as mine. Let's rewrite this as the cube root of 3 times 3 times 3 times 3, x to the 5th, y to the 7th, plus the cube root of 2 times 2 times 2 times 3 times x to the 8th, y to the 4th. Again, if you're not sure, multiply all this out, you should get 24 and 81. Now we're looking for groups of 3. This is the cube root of 3 times 3 3 times, which is 3. We have a 3 left on the inside. Don't forget the index is still 3. 5 divided by 3 is 1, remainder 2. I have x to the first on the outside, x squared on the inside. 7 divided by 3 is 2, remainder 1. We have y squared in the front. We have 2 groups of 3 with a remainder of 1 on the inside. For the second part, we have 3 groups of 2. The cube root of that is 2 with a 3 left on the inside. Notice the index is still 3. And we're looking at groups of 3 for x to the 8th. We'll divide 8 by 3. That's 2, remainder 2. I have an x squared on the outside with a remainder of 2 on the inside. 4 divided by 3 is 1, remainder 1. Again, we're looking for groups of 3 for y to the 4th. I only have one group of 3 with a remainder of 1. And so we have now 3xy squared times the cube root of 3x squared y to the first, or just y, plus 2x squared y times the cube root of 3x squared y. Now we can simplify it a little bit further. Notice they have the same factor here. So I could extract the factor out. This is 3xy squared plus 2x squared y times the square root of 3x squared y. Since they have a common factor, we can factor that out to the front or to the back. Either one is equivalent. In example 8, let's simplify the radical. This can be written with our exponent rule as x to the m over n is the nth root of x raised to the m. I can write this as 2 raised to the 5 over 10. And this is equivalent to 2 raised to the 1/2, or the square root of 2. For part B, I am looking for groups of 3. We can divide the 9 by 3, that is 3. We can divide the 18 by 3, that's 6. This is the same as a cubed b to the 6th. There is no radical left because we have no remainders. For part C, let's recall the formula is also equivalent to x to the m over n equals the nth root of x raised to the m. Notice that the index is still the same, but inside the radical we have an m. So the m could be on the outside with the parentheses or inside. I can rewrite this as the 6th root of 4 raised to the 2/3 power using this formula. Now we could use that formula again to rewrite this as 4 raised to the 2/3 power divided by 6. Now I can rewrite this as 4 raised to the 2/3 times 1 over 6 by multiplying by the reciprocal. And this is 4 raised to the 2/3 times 6 which simplifies to 2/18. We can simplify the 2/18 to 1/9, and we could rewrite this as a radical as the 9th root of 4. For example 9a, I'm going to use the formula for the difference of squares. Recall a plus b times a minus b is equivalent to a squared minus b squared. This is the formula for the difference of squares. This is our a, this is our b. This is our a, this is our b. So we can use our formula to rewrite this as a squared minus b squared. I have the square root of 11 squared minus the square root of 17 squared. Now the square root of 11 squared is 11, and the square root of 17 squared is 17. This simplifies to -6. So it's very important that you memorize the formula for the difference of squares. It shows up quite often. For this example, unfortunately, we cannot use the formula because this is not the difference of squares, but I can simplify 32. 32 is 2 times 16, 16 is 2 times 8, 8 is 2 times 4, and 4 is 2 times 2. So use the factor tree again to break down 32. I know that the square root of 32 is the same as the square root of 2 times 2 times 2 times 2, 5 times, and we're looking for groups of 2. So this is equivalent to 4 because of the 2 times 2, and we have a square root of 2 left. So let's replace the square root of 32 with 4 root 2. This is 5 plus 4 root 2 times 3 minus root 2. And now we can FOIL. 5 times 3 is 15. 5 times negative square root of 2 is -5 root 2. 4 root 2 times 3 is 12 root 2. We're just multiplying the number 3 times the number 4 with the square root of 12. 4 times root 2 times negative root 2 gives me 4 root 2 times negative root 2. Now let's simplify. This is 15. I can add these two together. That's 7 root 2. Now what is the square root of 2 times negative square root of 2? That's equivalent to the square root of 4, because 2 times 2 gives us 4. But there was a negative, so let's make sure that there's a negative in the front. We'll replace this with a negative in the front. So we have 4 times the square root of 2 times negative square root of 2. That negative will be transmitted to the front here. Square root of 2 times square root of 2 is the square root of 4. Again, recall the square root of a times the square root of b is the square root of ab. Now what's nice about the square root of 4 is that's equivalent to 2. We have 15 plus 7 root 2 minus 4 times 2. Again, there's an invisible multiplication between these. This simplifies to 15 plus 7 root 2. Negative 4 times 2 is -8. Let's collect like terms. 15 minus 8 gives us 7. We have 7 plus 7 root 2 is our solution. So take your time with the foiling. Make sure you understand where each of these numbers come from. In example 10, I want to rationalize each of the denominator, which simply means we do not want any radicals in the denominator. No radicals in the denominator. So we'll have to get rid of any radicals in the denominator. Now for part A, we have a square root of 7 on the bottom. We can't allow that to happen. We have to rationalize it. So how would we get rid of the square root of 7? We'll need to multiply it by something on the top and on the bottom. To do this, we'll use 7, the square root of 7. We have 2 root 7 on the top, and then on the bottom, root 7 times root 7 is the same as root 49. Well, I know what the square root of 49 is, that's 7. So the bottom simplifies to 7, but the top stays the same. So we have 2 root 7 over 7. Don't feel tempted to reduce the 7 with the 7. Don't do it. We have one that's in a radical and one that's outside. So stop here. This is the simplest we can make it. For part B, let's use the formula. The nth root of a over b is the nth root of a over the nth root of b. I can rewrite this as the cube root of 4 over the cube root of 9. Now we'll have to decide what we need to multiply the top and bottom by. A lot of people make the mistake, oh, we need the cube root of 9 on the top and on the bottom. That is incorrect. You do not need a cube root of 9 on the top and on the bottom. We want to make sure that the radical disappears. In part A, notice that we have 2 7s, and the square root of those 2 7s was 7. Here we're looking for the cube root of 9. So we need a group of 3. I'm going to actually add the cube root of 9 times 9 to the bottom, and we'll multiply the cube root of 9 times 9 on the top. The reason for this is we're looking for a perfect group of 3 so that there's no more radical on the bottom. This is simplified as the cube root of 4 times 9 times 9 over the cube root of 9 times 9 times 9. Notice on the bottom we can simplify this. This simplifies to 9. So the cube root of those 3 9s is just 9. Now for the top, we can break it down a little bit further. I can rewrite this as the cube root of 2 times 2 for the 4, and 3 times 3 for each of the 9s. We're looking for a group of 3, and so I can simplify this as 3 cube root. We have 12 left on the inside over 9. Now, we can actually reduce the 3 and the 9. That's perfectly fine. That reduces to a 1. That reduces to a 3. This is the cube root of 12 over 3. Now stop here. Don't feel tempted to reduce the 3 and the 12. This one's in a radical. This one's outside. Stop here. These answers are good. Again, we'll try this problem out. I'm going to multiply the top and bottom by something to get rid of that radical in the denominator. Now I know the index is going to be 3 because these all have an index of 3. Now, how many more a's do we need to get a perfect group of 3? I need only one more because 2 plus 1 gives us 3. How do I get this to be a group of 3? I need one more b, so we'll use b to the first. And since we multiply the bottom by this number, in order to make it the same value, we'll still have to use that on the top. So let's simplify this as the cube root of a to the 6th, because 5 plus 1 gives us 6. And b to the first times b to the first is b squared. That's the numerator. We're adding 5 plus 1 and 1 plus 1 to get these exponents. For the bottom, we have the cube root of a to the third power, because 2 plus 1 gives us 3, and b to the 6th power, because 5 plus 1 gives me 6. Now, the reason we chose this is because we want a perfect group of 3 on the bottom. So let's make sure that's the case. 3 divided by 3 gives me 1. There is only one group of 3 for A. 6 divided by 3 is 2. This is b squared. Now for the top, I can simplify this as a squared, because 6 divided by 3 gives us 2. We have left inside the cube root of b squared, because I can't divide the 2 by the 3. Now we'll simplify. Don't feel tempted to reduce the b squared and the b squared. This one's in the radical, this one's outside. But it's okay to reduce the a squared and the a. One of these a's reduces with one of these a's, leaving one left. And so our solution is a cube root of b squared over b squared. Again, don't feel tempted to reduce the b squareds. One is in a radical, one is outside. So make sure you understand why I picked a to the first, b to the first. We want groups of 3. If we get groups of 3, then we know the radical disappears. If this was a square root, I would look for groups of 2. If this was a fifth root, I want groups of 5. So the radical on the bottom will disappear when we divide these by the index. For example 11b, let's use the quotient rule to simplify this as the fourth root of 6 over the fourth root of x to the 8th minus the fourth root of 3 divided by the fourth root of x to the 16th. I can simplify each of these denominators. 8 divided by 4 is 2, and that is x squared on the bottom. There's no remainder, so I don't have a radical left over. This also simplifies in the denominator. 16 divided by 4 is 4. We have x to the 4th in the denominator. I can get common denominators by multiplying the top and bottom of this one by x squared. That will give me an x to the 4th, and I can add these two fractions. This simplifies to x squared times the fourth root of 6 over x to the 4th. That's what I want. I want the denominator to be x to the 4. And now we can finally subtract these two. This is equivalent to x squared, fourth root of 6, minus the fourth root of 3 over x to the 4th. Don't feel tempted to reduce the x squared and x to the 4th, because if you're going to reduce that, you want to make sure you do it to all of the terms, and in this case we can't do that. So this is our simplified expression. This looks really ugly, but this is our simplified expression. Please don't feel tempted to reduce the x squared and the x to the 4th. In example 12, notice that in the denominator we have a binomial denominator. To get rid of this, you have to use what we call the conjugate. The conjugate of a plus b is a minus b. So if this has a plus sign, use a minus sign between. The conjugate of a minus b is a plus b. So if this has a minus sign between, use a plus b. So in this case, I have a plus, so the conjugate is 3 minus the square root of 5. So we'll multiply the top and bottom by 3 minus the square root of 5. For the top, I'll have to distribute. This is 2 times 3 minus 2 times the square root of 5. On the bottom, notice that these are the difference of squares. So I could use our formula from earlier. A minus b times a plus b is a squared plus b squared, the difference of squares again. This can be written as 3 squared minus the square root of 5 squared. 2 times 3 is 6. We'll leave the 2 root 5 alone. 3 squared is 9. And the square root of 5 squared, that's 5. The bottom simplifies as 4. This is 6 minus 2 root 5 over 4. Now notice each of these has a factor of 2, so it's okay to reduce them. I'll divide everything by 2. I get 3 minus root 5 over 2. And that is simplified. So when you have a binomial denominator, make sure you use the conjugate for it, then simplify.